Hi everyone, welcome to this YouTube channel MathsSpark. The next video on Riemann integration topic. Today we are going to discuss oscillatory sums. In the previous topic, we defined the bounded functions. For the bounded functions, how one can calculate the upper sums, lower sums that we know upper Darboux sum, lower Darboux sums. The notation for upper Darboux sum is UPF, and it is defined by the summation of all supremum on subintervals I from 1 to n. If you are having partition P like this, x0, x1 and xn, these are the n plus 1 points of partition closed interval AB, in which x0 is A and xn is B, and I denote the rth interval as xr minus 1 xr and delta r as length of this rth interval, delta r as length of this r interval. Since originally your function from closed interval AB to real line, all are real valued functions, it is bounded, so it has to be bounded on each of its subinterval, otherwise boundedness on the total region will be fail. So on each subinterval it is bounded. Bounded means function has supremum and function has infimum. So let us, this mi denotes infimum on ith interval, or okay, I'll call r notation mr on rth interval, and capital Mr denotes the supremum on the same interval. The function has highest value, that is supremum value, in IR interval denoted by the capital letter Mr, and the infimum will be denoted by small letter mi. And on each subinterval you just multiply this infimum and supremum by the length of the interval. So when you consider the supremum, it will become upper sum, the upper sum, and when you consider the infimum, it will be the lower sum. So that is mi delta r from 1 to n. So this is known as upper Darboux sum and this is known as lower Darboux sums, and all, since function is bounded, so all upper sum and lower sum has to be exist, because on each subinterval it is bounded and length of each subinterval can be calculated. So upper Darboux sum and lower Darboux sums can exist, is guaranteed due to the boundedness of the functions. So we want to define the oscillatory sum. So let me take one example, a simple example. I will take the straight line f of x equal to just x. Straight, you can take any curve also. I'll just take straight line, and the interval is 0, 1. So let us, I have partition as 0, 1 by 4, 1 by 2, 3 by 4 and 1. So this is the partition. So what is the first interval? It is 0, 1 by 4. Second interval, it is 1 by 4, 1 upon 2. Third interval I3, it is 1 by 2, 3 by 4, and fourth interval I4, 3 by 4 to 1. Keep this in mind, these intervals. And let me explain the upper sum and lower sum graphically. So this is your x-axis, this is y-axis, and it is the origin, and I will draw the graph y equal to x. So straight line only on interval 0 1 I will plot, only on closed interval 0 1 I will plot that line on which y and x coordinate are same. Assume that this is straight line. Okay, and now you have consider the partition for that. So this is the 0 point, so half between this 1 by 4 and here 3 by 4. Okay, let me write 1 here because closed interval 0 1. So these are the partition points. Now as you can see, the function is increasing on this subinterval. On this subinterval, what is the least value of the function? It is 0. So m0 is written as 0. What is highest value? m1. Highest value of m1 is 1. So I am calculating 0 multiplied by length of this interval is 1 by 4. So area 0. So this is the first rectangle. And nextly, what is upper sum for this particular region? It is like, this is the area of this rectangle. This is the highest value, and it is 1 by 4. 1 by 4 multiplied by the length, that is 1 by 4. So 1 by 16. This value has 1 by 16, and this rectangle has 0 area. Similarly, if I consider this interval, I consider this interval. On this region, this is the highest value of the functions and this is the lowest value of the functions. So m1 delta 1. Okay, I should write, I should start with m1 here, and then second m2 delta 2. So the small m1 is this value 1 by 4. So this is 1 by 16 value. So your m1 delta 1 becomes 1 by 16. Sorry, this will be m2. m1 delta 1 becomes 0. m1, this is the first rectangle, 0 area rectangle. This is the second. And as per the upper sum concern, what is the highest value in this? 1 by 4 and 1 upon 2. The function has 1 by 2 as the highest value because it is increasing, and at this point function becomes the highest value. So the area of this rectangle is nothing but your capital M2 delta 2, this one. And similar likewise I calculate for all. So this is lower Darboux sum for particular subinterval, and this is the upper. This is the lower and this is the upper. So by this example I want to define what do you mean by oscillatory sum. You can see the upper sum is always greater than or equal to this because mi is always greater than or equal to mi for all this, and just multiply by delta I and summation, that is UPF is always greater than or equal to LPF. So the difference UPF and LPF is always positive, and this see this is the difference. See, this is the difference, and sum of all this difference, see this is the difference for third interval and this is the difference for this interval. So sum of all this shaded region, the shaded region is nothing but oscillatory sum. Sum of all this shaded region is called oscillatory sum. So let me define by this. One can calculate for this example also. So UPF for this will be the summation mr delta r from 1 to how many points I have taken? x0, x1, x2, x3, x4. 4 points I have taken, and LPF is summation r from 1 to 4 mi, okay, mr delta r. So upper sum we can calculate, lower sum we can calculate, and the difference of these two, since UPF is always greater than LPF, greater than or equal to, so the UPF minus LPF, the difference of these two will be r from 1 to 4 mr minus small mr into delta r. If you simplify this, so I will call this term as OR, oscillation for first, this one O1, this term is your O1, this is second oscillation, third oscillation and fourth, and each oscillatory difference multiplied by the length interval is nothing but oscillatory sum. So for this example, it is homework to you that you can calculate for this. It can be easily calculated because, okay, I will calculate upper sum. What is the upper sum for this first interval? It is the 1 by 4 is highest value in the first interval, 1 by 4, and multiply by the length is constant, that is 1 by 4 for all. Then in the second, it is 1 upon 2, 1 by 4 to 1 by 2. So 1 by 2 is the highest value, 1 by 4 is the length. In the third, 3 by 4 is highest value and 1 by 4 is multiplied. And in the last, 1 is the highest value multiplied by 1 by 4. The sum of all these upper sum. Likewise, for the lower Darboux sums, first area is 0, second is 1 by 16, third is 1 by 2 multiplied by 1 by 4, and the fourth is 3 by 4 multiplied by 1 by 4. So that is lower sum. So you can see the difference of upper sum and lower sum is this much. So that difference is called as the oscillatory sum. So let me make the formal definition of this oscillatory sum. It is very easy and simple to understand. The UPF minus LPF. What is UPF? It is summation r from 1 to n if having n plus 1 points mr delta r minus small mr delta r r from 1 to n. So this is going to be summation r from 1 to n, the capital MR minus small mr delta r. So it will be denoted by OR, that's oscillation on rth interval. So what is this OR? OR stands for oscillations for rth interval, mr minus small mr. So this will be. So this is the oscillatory sum. It is denoted by omega p comma, since in the physics we denote oscillations by omega. So omega pf is the oscillation for this. And keep in mind, as for each subinterval, on each subinterval IR for all x, so this is always going to greater than or equal to this. If I multiply by length interval, which is fixed, will be same, and if I make summation of this, this will be greater. So this sum is nothing but UPF and this sum is nothing but ELPF. So you can see the difference of this is always positive, or I can say non-negative if they may be equal. So this is always positive, that means oscillatory sum is always non-negative. Keep this result also in mind, oscillatory sum is always non-negative. So in the next lecture we'll see the important properties concerning upper sum, lower sum, this oscillatory sums, all those things by geometrical examples and all. Till then, thank you. Subscribe and like the channel.